All right, so our next topic is springs. And springs, this is something that we want to talk about because it's treated in Chapter 8. We're not going to talk about it in any detail right now, but we will need this information when we get to Chapter 14. Now here's the crucial piece of information in Chapter 8 about springs. If you take some sort of a spring, okay, and you stretch it or you compress it, and so you change its length by an amount delta x, there's a restoring force that is equal to a constant k, which is the spring constant, times the amount that you stretched or compressed it. And the spring force is always pulling against you. If you pull it to the left, the spring pulls back to the right. If you compress the spring to the right, it pushes back to the left. The force is always opposite of any force you apply. Now let's take a look at a quick problem. And I'm always looking for like interesting things to ride and also interesting things to wear on my feet. I have this obsession with being able to hop like a kangaroo, and we'll talk about why when we get to Chapter 11. But I got these shoes, and the shoes had springs in the soles, okay, and the shoes had springs in the soles. And I looked up information on the manufacturer's website and saw what the spring constant was, and it's 30 times 10 to the 4th newtons per meter, okay? Question, if my weight is approximately 700 newtons, how much do the soles compress if I stand on one heel? Okay, how much do the soles compress when I stand on one heel? Well, the first step to solve this problem is to strategize. And we're going to say we're going to treat this as a spring force problem. Okay, the springs in the heels are springs. And if I know the compression, I can find the spring force. And if I know the force, I can find the compression. And so we're going to treat this as a spring force problem. And if we know it's a spring force problem, when we prepare, it's basically telling us we're going to use this relationship right here and see how we can extract the different pieces of information. Now here's the thing, if we have the spring, okay, I have the spring in the heel, and I'm standing on it, the spring is pushing up on me with a force of 700 newtons because that's my weight. And so as a consequence, I am pushing down on the spring with a force of 700 newtons. That's the F which is going on here. And as a consequence, the spring will shorten. It will shorten by an amount delta x. And that is in fact what we're looking for. And so that's my preparation and sketching this out so you're absolutely sure what is the force, what are you looking for in terms of the stretch or compression of the spring. That's a crucial piece of the puzzle. With our preparation in hand, we are ready to solve. And solving, we're going to use our basic expression, which says the force of the spring is equal to k times delta x. Delta x is in fact what we are looking for. K is the spring constant. That's 30 times 10 to the 4th newtons per meter, which is not trivial to get off a manufacturer's website. And then we know the force of the spring. That's 700 newtons. It is pushing back we're pushing on it with a force of 700 newtons. It's pushing back with a force of 700 newtons. And so we have everything in hand to solve delta x. And if we do that, we get a compression of 2.3 millimeters. Now that's only about 1/10 of an inch. So that's a tiny, tiny compression. And my assessment is, does this make sense? That's the thing that we always ask. Well, I own these shoes, and I can tell you when I stand on one heel, they don't compress very much. They have springs in the heels, but they really don't compress very much. As a consequence, they don't store very much energy. And they were purported to basically put literally some spring in your step when you are walking or running and get you some energy returned and some rebound so that you can hop more like a kangaroo than plod like a human being. Does it work? The answer is it does not. These shoes are not helpful, and actually they're bad in some key ways that I'll talk about later. But my assessment is this is in fact consistent with my understanding of the way the world works. Now it's not just springs that exert restoring forces when you stretch them or you compress them. You can also have it when you stretch solids. If you push on a rod or pull a rod, it will stretch or compress. Okay, and the amount that it stretches or compresses is given by this expression right here, okay? And this is the force that you've applied divided by the cross-section area of a rod or whatever is equal to this thing called the Young's modulus times the change in length divided by the length, okay? And this quantity right here, F over A, is known as the stress. This quantity right here, delta L over L, is known as the strain. So it's a stress-strain relationship, okay? And here's just a reminder of that relationship in the kind of situation where it might occur. You have these people putting a really, really large force on the rope, and as a consequence, the rope is going to stretch ever so slightly. Now, before we do a problem, I want to talk about the values of Young's modulus, okay? And we've got a couple of different types of materials. We have things here like iron and steel, and kind of like, these are sort of like minerals and stuff. Not very stretchy or compressy. On the other end of the scale, we've got these things like spider silk, tendon, blood vessels, and spongy bone. Very, very stretchy materials. And so we have things which are much more elastic. And the elastic properties I want to bring up now. We're not going to talk about in detail now, but we'll use them when we get to talking about energy. These are going to be really important for us. For instance, tendons, Young's modulus is much, much smaller than it is for like steel. Okay, steel does not stretch as much as tendon, and as a consequence, you can store energy. Same thing with spider silk. Both those are points we'll come back to later. And let's take a look. You have discs of cartilage between the segments of your spine, as you know, and their Young's modulus is way smaller than the things we even saw on the table. 15 times 10 to the 6 newtons per square meter. Very, very small. That makes, they're very, very squishy. They're very, very squishy. And you want them to be. You want them to compress a little bit. They're going to be a little bit springy, okay? So the question asks this: if a disc in your spine supports half the weight of a 65 kilogram person, by how much does it compress? Our strategy is we're going to treat this as a stress-strain problem, okay? I apply a stress, I apply a force, and I want to know how much strain results from this. How much will the disc compress? So it's a stress-strain problem. With the stress-strain problem, we can use the relationship which we've seen previously, and preparation is basically seeing what do we have to use for the different variables in this term. Okay, now the force that's applied, okay, the force that's applied to the vertebra is basically 1/2 the weight of the person, because we're told that a disc is supporting half the weight of a person, and so it's being pushed on with half the weight of a person. It's pushing back with half the weight of a person. So this is 1/2 of the weight of a 65 kilogram person. So 1/2 times 65 kilograms times 9.8 meters per second squared. Okay, that's my expression there. The cross-section area is given in the problem statement as 6.5 times 10 to the minus 4th meters squared. So that's what goes here. L is the thickness of the disc. It's basically the length. What is the length, or in this case, the thickness? Oh, and we're given the thickness. The thickness is 8 millimeters, okay, which we're going to turn into 0.0080 meters, okay? Young's modulus is this value right here in the equation, and we're given that. We're told the Young's modulus is 15 times 10 to the 6 newtons per square meter. Heavens, the only thing we don't know in this expression is in fact delta L. That is like how much the disc compresses by when you apply that force to it. And so we have everything in the equation except for that one. And basically the preparation just comes in recognizing what all the terms in the relationship are and finding the relevant numbers that we're going to use for them. Okay? So we're ready to solve. And solving is basically just taking all of those numbers and putting them in the equation. And if I do that, I get a delta L of about 0.25 millimeters, so 1/4 of a millimeter. Okay, that's a really, really tiny stretch. Okay, that's about a 1/100th of an inch. And in fact, we expect that to be true. Okay, the discs in your spine are going to compress more when they're experiencing more forces, when you're kind of like undergoing strenuous activities or you're lifting something. But under normal circumstances, we don't expect them to compress very much. So my assessment is, does this seem reasonable? Yes, slightly springy, but not too much. If they're really, really sloshy, you would have a certain height. When you're lying down, you would stand up and they would compress a lot, and you wouldn't be. Yeah, so this makes sense, absolutely. Now, this set of topics which we dealt with in the slide is not something we're going to deal with in any detail right now, but I wanted to show it because it is stuff we will need when we get to chapter 10 and we start talking about energy. But the next piece of the puzzle we're going to look at is momentum. And in momentum, we're going to be considering things that happen really, really quickly where the forces are really, really large. Fun topic with lots of applications. That's what we're doing next.